about solids and liquids. What's special about a gas? Why do we kind of keep it separate, have its own chapter? What's different about gases? Yes, they don't have a definite shape or volume. So what does that mean? What makes things a little trickier about talking about gases because of that?
Measuring.
Yeah, measuring, and basically, I mean, it's harder to measure out gases. If you want to do a reaction where a gas is one of your reactants, think about how you would do that in lab. Like last week we did the chemical reactions labs. It was pretty easy. We had dropper bottles of stuff, and you'd like put them together, and that was relatively easy. Now imagine if one of those reactants was a gas, like hydrogen gas or something. You couldn't really do that. It'd be hard to weigh it out. You couldn't use a dropper. You could use a balance, but you'd have to contain it in a balloon or something like that first. Then you'd have to somehow get it into your reaction. So you'd like bubble it through, but then what if it doesn't react? It just kind of goes through. So gases present a lot more problems from a chemical standpoint because of these different properties. So we treat them a little bit differently. We measure them a little bit differently. We use some different quantities when we're talking about reactions of gases. And so that's really what this chapter is talking about. So are you excited about gases? Is it going to be a fun chapter? Not really. Does anybody have like bad gas right now? It's kind of different. You know, hopefully not. All right, so the main thing that's different now that we haven't talked about before is pressure. Gases are often talked about in terms of their pressure, and we'll go through why that is when we talk about the kinetic molecular theory, like what causes that pressure. But that's a nice way of understanding how much gas we have, because the more gas that's in a particular container, the greater the pressure it's going to exert. So to do that, we have to deal with our units of pressure. That little picture there is something called a barometer. So you fill a tube with mercury, and then have it kind of in a bath of mercury. Don't actually do this, it's a really bad idea. Mercury is really poisonous, so we don't really use these anymore. Has anybody ever messed with mercury at all? Just with mercury? So we can get it out at some point. We have a little bit of it sealed up. The problem with mercury, and like in the old days, they used to play with it in chemistry classes because it's kind of cool because it's like a silvery metallic liquid, and you could like roll around on the table and like split up into droplets. It looks very science fiction-y, and it's kind of heavy. The problem is it's really poisonous, and even if you're careful and you wear gloves and stuff, mercury has a significant vapor pressure, which means that there's always vapor coming off of it. So even if you're being careful, you're inhaling mercury vapors just when it's out. That's why, like, if we break a mercury thermometer or something, maybe we don't use them here anymore, but if you were to break a mercury thermometer, it needs to be cleaned up right away with special equipment to make sure that those vapors don't get into anybody's lungs. So don't make this device, but this device was at once made. The reason they used mercury was because it was so heavy. So it was a good way to measure this kind of pressure. And so if you take a tube and you evacuate it, you get all the air out of it, and you invert it in this bath of mercury or water or whatever, the mercury or the water is going to go up the tube. Do you sort of see that? Like if you were in the bathtub and you sucked all the air out of something and then like stuck it in there, the water would fill back into it. But one thing that's interesting is think about what's pushing the water up there. So it's not like it's just going up there because there's space. It's actually the atmospheric pressure. So the atmosphere is pushing on all the water around it, which is then pushing that stuff up the tube. And that happens with mercury as well. And that was kind of the original idea, or what led to some of the original ideas of pressure and atmospheric pressure. That something has to be pushing this thing up this tube, and the thing that's pushing it is the atmosphere. So we have this standard unit called an atmosphere, and that's the unit that we'll use most when we talk about pressure, abbreviated 1 atm, and that is the atmospheric pressure at sea level. So it's defined as the pressure that the atmosphere exerts at the lowest place on Earth, which is sea level. I mean, you can go below sea level, but that's what we define that way. So that's called an atmosphere. And then we have all these other units for pressure that we can relate to an atmosphere, and we can convert among them, you know, using our normal conversion stuff. So we've got millimeters of mercury, which is kind of a weird unit because it's millimeters, so it seems like a length unit, but it's actually a pressure unit. The reason it says millimeters of mercury is because of that tube thing. So that's how many millimeters a tube of mercury would get pushed up by the atmosphere at sea level. There's this other unit called the torr, named after this guy Torricelli, who developed this barometer. That is kind of a weird unit. It's generally defined as being the same as a millimeter of mercury. It's not exactly the same, actually. It's a little bit different. A millimeter of mercury is defined by this, like pushing the mercury up the tube, which is not a great unit because it depends on things like temperature and where you are and the size of things, and because the density of mercury is going to depend on pressure or on temperature, depends on gravity. There's like too many variables. So a torr was kind of defined later as, let's just make a torr. One torr is a 760th of an atmosphere. So there are exactly 760 torr in an atmosphere. Millimeter of mercury, it's close enough. And they're the same out to like 7 decimal places or something. So we can just use them interchangeably. But technically, they're not exactly the same. All right. Pressure, we should note, if you don't know, is force over an area. So pushing a force over an area. It's like if you wear shoes that have like pointy heels on them and you go walk on soft ground, you'll like sink in. But on wider shoes, you won't sink in. Or if you wear snowshoes, you could step on top of snow. That's the same force because it's still your same weight, but because it's over different areas, there's different amounts of pressure. So the SI unit is Newton per meter squared. A Newton is force, and a meter squared is the area. And that's called the Pascal. 1 Newton per square meter is the Pascal. So that's kind of like the metric unit used in physics, that kind of thing. We'll use it a little bit as well. And then there are the English units, or imperial units, inches of mercury, which is the same idea as the millimeters of mercury pushing up the tube, but in inches instead of millimeters. Anybody know where that comes in? Where we use inches of mercury as a measurement? That's how we usually measure what we call barometric pressure, like the pressure of the atmosphere. When you're talking about weather reports, or like you have a little thing up on your wall that has the barometric pressure, and you can predict if it's going to rain or not based on the changes in that pressure. Those numbers are usually reported in barometric pressure. So if you're on a weather website or something and it says it gives you the pressure, that's usually in inches of mercury. And then the last one is pounds per square inch, which is a common English measure in things like tires, right? Like your car tires. Anybody check your car tire pressure recently? Should do that pretty regularly. Make sure you do that. But those should be about 35 or so, depending on the car. We'll talk a little bit more about that. So the numbers that you need to know for this class is just this one, really. You need to know that an atmosphere is 760 millimeters of mercury or torr. We're going to go back and forth between those units a lot, so you should know that conversion. You don't have to know the numbers for pascals and inches of mercury and pounds per square inch. Those conversions I would give you if you needed them for anything. All right, so we can do a conversion problem there. We won't go through it because I know you can convert units, but you would do this the same way we've converted all other units. You figure out how you're changing, right? The one you want is on the top, and then the one you don't want on the bottom. Go from there. Nothing different, just a different kind of a unit. All right, so let's look at some gas laws. Actually, before I do that, give me a minute. I'm going to get some props. Yeah, take my props. All right, I guess.
Joe, we've been waiting like 4 weeks to do this.
Yeah. Well, no, not exactly. There's an even better one, but I don't know if we're going to get to it in time because we need liquid nitrogen for it. And because we started 2 weeks early, I don't know if we're going to get the liquid nitrogen, when like we get a shipment in for all the other classes. But if we do, that'll be fun. We can make ice cream with it too. We'll see.
With the dried ice. Is that what you said?
Liquid nitrogen.
Liquid nitrogen? Yeah. So fun.
All right, so some balloons. Are you all familiar with balloons? They stretch and like hold air. Okay. So I got some balloons in here. And there's one hanging from the top. There's a seal down here. So that should make a pretty good seal with this jar thing. And I'm going to hook up this tube to the vacuum, and I'm going to evacuate the container. And as I evacuate the container, what do you see is happening? Anybody? For the people who can't see. Can everybody see? So what's happening?
So did you take the air out of that, right?
Yes, so this is evacuating the container, taking the air out. So how are we inflating the balloons if we're taking the air out? We're not exactly inflating them, right? They're getting bigger, but it's not because air is going into the balloons. So what is happening?
Yeah.
Yeah, so we're changing the pressure in the container. We're lowering the pressure in the container. And so then what's happening inside the balloons? The balloons, the air inside was originally at regular atmospheric pressure. So if we lower the pressure on the outside, then the balloons get bigger because the pressure is also going down on the inside. And depending on how strong our vacuum pump is, at some point they will stop. But what I can do here is close this valve up, pull this thing off. And then as I let the air back in, what's happening then? The atmospheric pressure is greater than the pressure inside there, right? Because I pulled some of the gas out. So the atmospheric pressure is going to push gas in here, fill that container back up with air, and we would expect the balloons to go back to their regular size. But no amount of air has changed inside the balloon, right? The balloons still have the same amount of air. They're sealed. All right, so now we see it. So the balloons didn't inflate, but they did get bigger. The volume of the balloons changed. We'll let it go for a little bit longer while we talk about the effect behind that. if that plastic lid were compromised in some way, it could really cause some damage. It could actually implode because the pressure on the outside is so much greater than the pressure on the inside. All right, that's an expression of what we call Boyle's law. Well, Boyle's law, remember the difference between laws and theories? What is the difference? Yeah, law is like an observation and the theories behind it. So we're going to go through a bunch of what we call gas laws, which are just observations. So we'll start with the first one, Boyle's law. It's a set of observations, really. Boyle's law. Pressure and volume, the product of pressure and volume are constant. So as you change one, the other one changes to compensate for it. Notice that doesn't say why it happens. At the end of all the laws, we're going to go into the theory of what is happening with the gases that causes this. But for now, it's just the law. And Boyle's law says exactly what we see here. We change the pressure, the volume changes accordingly at constant temperature. So when we decrease the pressure, what happens to the volume? Does it go up or down? Increases, right? The balloon gets bigger as the pressure gets lower. So that's what we call an inverse relationship. Or we would say that pressure and volume are inversely proportional. Okay? A couple ways that we can just kind of rearrange this algebraically. All right, so here's our law, PV equals K. Pressure times volume is constant. We could make that say pressure equals something divided by volume. So K is just some number. It's going to change depending on the gas, depending on all kinds of stuff, the temperature. We'll get into that later. Or we could say that volume, K over P. Think about mathematically what that means, that if one gets bigger, if the P gets bigger, the V on the bottom has to get smaller so that both sides stay equal because of the equality. And then another way sometimes we say this is that you may have seen this before. Excuse me. Since pressure times volume has to be constant, as long as everything else stays the same, that means that if you change one of them, you can figure out what the other one is going to be in the new situation because the product of both of them has to be constant. So in the third situation there, we're saying we have an initial pressure and volume. If we change a pressure, we can find the new volume. If we change the volume, we can find the new pressure. Yeah. So that's an example of changing the pressure first and having that affect the volume. We could also do it the other way where we change the volume and have that affect the pressure. Here's an example of that. So anybody know what this is supposed to be? Yeah, this is supposed to be like your lungs. And so this is kind of how your lungs work, how breathing works. If I close the hole on the top, like I'm shutting my mouth and nose or something, and I try to pull this down to change the volume, nothing really happens because if I want to change that volume, that means I'm also changing the pressure. Right? If I pull this down, I'm increasing the volume. What does that do to the pressure inside? It decreases it, and so it becomes difficult to do. Right? Same thing this way. If I try to push up, I can't decrease the pressure until I release my finger to let that pressure, increase. Increasing the pressure. So this is how breathing works. We can talk about it in terms of changing pressure and volume. So when you inhale, you're not sucking air in, actually. What you're doing is you're changing the size of your chest cavity. You're increasing the size of your chest cavity, which does what to the pressure? Changes it. How? Decreases it. Yeah, if you increase the size of your chest cavity, then the pressure inside there is going to go down. If the pressure goes down, you've now created a pressure differential, meaning there's less pressure, lower pressure inside your chest than outside. So the atmospheric pressure is going to force air into your lungs to equalize that pressure out. And that's what's happening here. And if I use my finger, I can kind of stretch this to decrease the pressure. And then as soon as I open it up, the air rushes in to equalize that. So then when we exhale, we're doing the opposite. We're using our diaphragm to make the volume of our chest cavity smaller, to make the volume go down. That increases the pressure inside and causes the air to go out to equalize the pressure. And you can feel that in your own body if you don't let any air out or in. Close your mouth, and you don't have to like pinch your nose, but just kind of close it up with the valves in there, and then like push out really hard, like you're trying to poop or something, and you could feel that pressure. And then you can do the other one where when you're inhaling as well, where you like pretend you're taking a breath in, and you can feel the pressure going down inside and kind of trying to pull all of your organs because it doesn't want to do that. So that's Boyle's law. If we plotted that, it would look something like this, where we have a pressure increase along the x-axis and then the concomitant decrease in volume. Okay, so see if you can do this. Sulfur dioxide is, we've got a 1.53 liter sample at this particular pressure in pascals. If the pressure is changed to this at a constant temperature, what will be the new volume of the gas? So the first thing that you should note on this is when you ever see problems like this, think about what the new number is going to look like. In other words, we can imagine our balloons, we can think back to things, and we can say, well, is this going to be bigger or smaller? So what happened to the pressure if it went from 5.6 times 10 to the 3 to 1.5 times 10 to the 4? The pressure went up or down? Up, right? Got bigger. 5.6 times 10 to the third, 1.5 times 10 to the fourth. Watch that exponent. So the pressure went up. So what should the volume be? Yeah, volume should go down. So do that calculation and see what you get. All right, so what'd you get? What? Does that make sense with what we said before? I think so, right? We said it was going to, we don't know how much it's going down, but we know that the volume was going to go down. So we should have less volume than we had before, and we do have that. Now let's think about units. Do units matter here? They do. Yeah, units always matter. How do we know if we can just do this calculation or if we have to convert some units first for this type of a problem? Anybody know? Did you have that question at all when you're doing this question with this problem? Like, do I need to convert anything? So the only thing you need to know for these types of problems is that the units need to stay constant. Like, they need to not change. So if we have pascals on the left and pascals on the right, we're good. If we have atmospheres on the left and atmospheres on the right, we're good. If we have torr on the left, torr on the right, we're good. Same thing, liters, liters, milliliters, milliliters, gallons, gallons, doesn't really matter because it's a proportion. It's saying these two things multiplied together are always constant. So as long as we have them the same, that's all we need. In this case, we had that, so it wasn't an issue. When we get into the ideal gas law, that'll change a little bit, but you'll see that. All right, so here's the other one that I wanted to, that I will demonstrate if we get our hands on some liquid nitrogen later in the semester. This is called Charles' law, where there's a relationship between volume and temperature. So as temperature increases, volume also increases. Anybody know what the name of that kind of a relationship is? If they both go the same way? That's called a direct relationship, or directly proportional. So we had inverse relationship between pressure and volume. We have a direct relationship between temperature and volume. So you've got now this kind of linear relationship as long as pressure is held constant. So that means that if we took one of these balloons, if we filled it up, or if we took one of these balloons and heated it up, what would happen to it? It would increase. So we increase the temperature, we increase the pressure. If we cooled it down, if we put it on ice or something, then the volume would decrease. Sorry, not the pressure, the volume. Yeah.
Like when you have like inflated like basketballs or like your tires in the winter or something.
Yes, exactly. Yeah. So if you have like, I mean, it's a little bit because pressure is involved there too. So pressure is not constant, but let's pretend that it is. In your tires, in the winter, when it gets really, really cold, you might see them get lower, and then you drive a while, and they look okay again. And that's because they were cold, volume went down. It's also an issue with pressure. So there's the same relation. We're not gonna. It does have a name. I don't know if we're gonna get into it. Yeah, I don't think we'll worry about it. Sachs law, which is pressure and temperature, but that's really what happens. Like, so, do you know where your tire pressure numbers are listed in your car? Where are they? Yeah, by the door. Everybody should know that if you drive a car, right? Down by the door, it's either the driver's side or the passenger side. There's a little chart. It tells you what the pressure for each tire should be, including the spare. And it usually says cold pressure. So does that mean you can only check your tire pressure in the winter? No, it just means before you drive. So like when you go out to your car in the morning or after it's been sitting for a while, that's the pressure that it should be at that time. Because then when you drive, the friction is going to heat it up a little bit, and you're going to end up with a little bit higher pressure. So when you go out to your car tonight or today after class, just check your tire pressure before you go home. Make sure everything's good. If you don't have a little valve thing, little pressure gauge, pick one up on your way home so you have it with you. Can you tell that I'm a dad? All right, so let's try a problem where we're dealing with pressure and temperature. This direct relationship. So the equation is going to be V equals constant times T. Or if we want to rearrange that, V over T equals a constant. So as the top gets bigger, the bottom has to get also bigger to compensate. And then we could also write this the way we did the other ones, where that quantity has to stay constant. All right. So this time we do have a unit requirement right here. And you can just assume for the rest of this chapter, anytime you're dealing with gas quantities, temperature always needs to be converted to Kelvin. Why is that? What's special about Kelvin? But yeah, there's no negative. So it starts at 0, just like all the other units. So like there's no negative volume, there's no negative mass, there's no negative distance really. So we need a temperature unit that also doesn't have that. I mean, imagine 0 degrees C, that's a totally reasonable temperature, right? That's the freezing point of water. But you can't put 0 degrees C in this equation because 0 would be undefined, because it would be 0 on the denominator. So yeah, so make sure your units are in Kelvin. and then try this problem out. Find the new volume of the gas after it gets heated up. So once again, let's make a quick check. Should this volume go up or should the volume go down? Should go up, right? Yep, because we're heating it up. So do that calculation, see what you get. .79. What you got? All right. Last one we're going to look at individually is probably the most obvious one of all, called Avogadro's law, which just says that if you keep volume, temperature, and pressure constant, then you're also going to have the same number of particles. Now, in the context of the time, that's a pretty amazing idea. This idea that the particles would be the same even though they were different masses and stuff like that. But for us, that kind of is obvious. Like if basically you're saying if you put more gas in, the volume goes up. If you want to decrease the volume while keeping the pressure the same, you got to let some gas out. That makes sense, right? If you want the balloon to get bigger, you put more gas in it. The thing that's interesting here is that this all talks about moles of gas and particles of gas and not mass of gas. And that's kind of unusual compared to other types of matter. We don't say that liquid volume is dependent on the number of moles of liquid there. We say that it has to do with the mass and the density and all this stuff. But with gas, what this essentially means is that we don't care so much about the mass. The properties like volume and pressure and temperature are all going to affect the number of moles. The other consequence of that is that gases are essentially interchangeable when it comes to this behavior. It doesn't matter how big the gas particle is. It doesn't matter if you have giant radon atoms or if you have tiny helium atoms. The gas properties are going to be roughly the same. Why do you think that is? Why are these properties of gases that we're finding not dependent on the actual size of the gas molecules? Why doesn't it matter how big the gas molecule is? Why does it only matter that it's a molecule or a particle and not how big it is? I mean, even a larger, like a molecular gas, like propane or something that has 3 carbons and 8 hydrogens is going to behave the same as a tiny helium atom. Why is that? Why doesn't the nature of the molecule or atom matter? No ideas? It's because in a gas, the space between the molecules is so great compared to the space that the molecules themselves take up. So in any sample of gas, unless it's at extremely high pressure, you have basically mostly empty space and just a tiny bit of actual matter. So what that matter is doesn't end up mattering as much as things like the volume and the pressure and the temperature. So that way, different types of gases are actually interchangeable. All right. So now we can put this stuff all together. Oh, well, let's do this problem because it's kind of interesting. So we have a 12.2 liter sample containing half a mole of oxygen gas. If the oxygen were converted to ozone, what would happen to the volume? It's kind of a weird idea because this is actually happening in a closed system. So let's say this is happening in a balloon. Balloon can keep it constant pressure by changing its size. So if it's in a balloon, we've got oxygen in there. The oxygen does a reaction inside the balloon. No oxygen comes in or leaves. And something's going to change with the volume. So to do that, we have to look at the equation. So oxygen gas is converting to ozone gas. And somehow this is changing the volume in the balloon. What's wrong with this equation so far?
You have to do the same conversion to help these together. Doesn't matter here.
We will, yeah. But not first. We got some other stuff to do. What do we need to do first? Yeah, we need to balance it. So let's balance this equation. Put a 3 here and a 2 here. Okay. So now we've got half a mole. Actually, we don't need to do the temperature in this case because it's constant. It's not changing. But we start with half a mole of oxygen. How much ozone are we going to end up with at the end of this reaction? Yeah, times 2 divided by 3, which is about 0.33, right? Okay. So if volume is directly proportional to number of moles, look what's happened here. We have a situation where we have something like this going on. So our initial volume is 12.2 liters, and our initial number of moles is 0.5. And we're going to solve for our final volume when our number of moles has decreased. So our new volume is 8.05, say 8.1 liters. So the volume's decreased from 12.2 liters down to 8.1 liters, even though no mass has changed, right? No gas has gone in or out of this balloon. But because the number of moles changed, the particles rearranged themselves, we changed the volume of the balloon. And that's really what is kind of remarkable about this idea, that it doesn't matter the nature, it doesn't matter the identity of the gas molecule, it just matters how many there are. Yeah. Using the molar ratio here. So for every 3 of these, we make 2 of these. So for 0.5 of these, 0.33 of these. The molar ratio is 2 divided by 3. So this times 2/3 is this. All right, so we combine all this stuff together into something called the ideal gas law, which I'm sure you've seen in previous classes, where we put all these quantities into one equation. P equals RTN over V, or as you've probably heard it. Anybody? Ideal gas law? Yeah. PV equals, did you say something? Yeah. So we've got pressure times volume. We know that's constant. And then we've got number of moles times temperature on the other side with this constant R. And R is a special number because it actually allows us to solve for these things instead of just saying that they equal some constant. So now we can solve for an absolute quantity of one of these, assuming we know the other ones. We don't just have to say, well, we started with this, and then we changed this, and what's the new one? We can actually solve for anything we want. Now that universal gas constant is very unit dependent. You'll notice it has a bunch of weird units in it. It has liters and atmospheres on the top, Kelvin and mole on the bottom. Now the Kelvin mole part probably won't give you much trouble because all our problems are going to be Kelvin and mole. It's the part on the top that we have to watch out for because volume has to be in liters and pressure has to be in atmospheres in order to use this particular gas constant. Now some people have different strategies for dealing with gas constants. You should know one. You should know them off the top of your head. You could just know this one and then make sure that you're always converting units to what you need. That's maybe the easiest way to do it. If you really like memorizing things, you can memorize some other gas constants when there are other units. So like if you convert that to millimeters of mercury, 1 atmosphere is 760 millimeters of mercury. So that number times 760 is going to be the R in liter millimeters of mercury per Kelvin mole. You know, you could do a milliliter version. You could, I don't know, whatever. There's a Pascal version that's used in some other stuff because of the newtons and meters. But you should know a gas constant so that you can calculate these types of things. All right, so let's try one. Sample this first one here. And this is really just, you know, simple algebra. You plug the numbers you know in and you solve for what you don't know. All right, so we've got pressure, we've got volume, we know R, and we've got temperature. So that means we're going to solve for moles. So when you look at a problem like this, first collect your data. You can do it that way, which is probably not all that organized, or you can write it out or something. And the main thing to check is just make sure your units all work out. So make sure that your pressure and your volume match with the gas constant that you're using, and make sure your temperature is in Kelvin. So is the temperature in kelvins here? No. So what should it be? 273, yeah. So we've got 1.5 atmospheres. And you know, as you get better at this and you get practice, take shortcuts, skip your units, whatever you want to do, but make sure that you are doing it right, you know. So what I would do, like on an exam, is write the whole thing out with all the units and all that, unless you're really pressed for time. That's going to help because you'll be able to see where you might make a mistake. And when I'm grading it, I'll be able to be more generous because I'll see, oh, you set this thing up right. You must have just typed something wrong in your calculator or whatever. Okay, so we've got the pressure times the volume. And then on the bottom, we're going to have the gas constant. And the temperature. This also gives you a chance to check, make sure all your units are canceling. So we've got liters canceling with liters, atmospheres canceling with atmospheres, kelvins canceling with kelvins, and the only things left is mole. And mole is on the denominator of a denominator, which means it's actually going to end up on top. That's going to be our unit that's left over here. 1.5 times 8.56 divided by 0.0821 273. So 0.57 moles. So as you'll see in a little bit, this is how we do stoichiometry with gases. We talked about the issues with measuring, things like that. Well, now we have an answer to that. If we know pressure, temperature, and volume, which are easy to get from experimentally, then we can figure out how many moles we have, and we can calculate the molar ratio accordingly. We also will sometimes go backwards with that. We're setting up an equation. We know how many moles of gas we want, so we got to figure out at whatever temperature we're doing the reaction, what's the pressure and volume of gas that I need to supply that many moles to my reaction. All right. Let's, oops. Let's take a break. Can work on these problems if you get bored during said break. Otherwise, we'll come back and start in about 15 minutes. Finish up talking about gases. Oh, it was 0.57. So what did you do first? You. Yes, probably. Yeah, we've got to get that grams to moles because ultimately we want to know the moles of carbon dioxide so we can calculate the gas properties. All right. So 152 grams of calcium oxide. .71 moles. All right. So then how many moles of carbon dioxide are formed? It's the same. How do you know?
The mole ratio.
Right. The mole ratio is 1 to 1. So we know we make the same number of moles of carbon dioxide. So far, just a standard equation stoichiometry problem like we did on the exam. Now is where it changes because that carbon dioxide that's formed is a gas. So we're not asked how many moles of carbon dioxide are formed. We're not asked how many grams of carbon dioxide are formed. We could do either of those based on what we've done before. But instead it asks, what's the volume of carbon dioxide produced? So how would we figure that out? Is there a way we can get from moles to volume?
There's a molar volume.
Yeah, a couple ways to do it. So there's a molar volume, which we haven't really talked about, but there's also what we did just talk about, which is the ideal gas law. So we've got PV equals nRT. We can rearrange that to solve for volume. So we've got, let's see if we've got all the information we need. We've got N, the number of moles. We've got R, you know that one. What about T and P? Sort of. There are temperature and pressure, so we have to be given them. Are we given them in this particular question? Yeah. Yeah, what does STP mean?
Standard.
Yeah, standard temperature and pressure. So a lot of times when we talk about these calculations, we're going to use something called standard temperature and pressure, which I think is defined up here somewhere. Yeah, right here. Which you should know is 0 degrees C, so 273 K, and 1 atmosphere. That's what we're going to call standard temperature and pressure. Another number that can be helpful, although you don't need it if you know STP, is this idea of molar volume. If you solve for 1 mole, N equals 1, at standard temperature and pressure, so if you plug into the ideal gas law, pressure is 1 atmosphere, temperature is 273 K, and N is 1, and you solve for volume, you always get 22.4. So that's called molar volume. There's 22.4 liters in 1 mole of gas, or 1 mole of gas takes up 22.4 liters at standard temperature and pressure. We could use that number for this problem. We don't necessarily need it because we have these other ones. So temperature is given, standard temperature, which is 273 K, and pressure is given, standard pressure is 1 atmosphere. Okay, so we put all those numbers together. And we get 2.71 times 0.08, whoops, 71 times 0.0821 times 273 divided by 1 is 60.7. So that's the liters of CO2 that we would form in this reaction. All right, see how that works? So you're going to use moles to do the stoichiometry part of the reaction. And then you're going to use the ideal gas law or the molar volume to calculate the volume. All right, so now see if you can do this one on your own. Same idea. The only change here is that the reactants are given in pressure, temperature, and volume. So you got to first set up the equation. Methane gas, if you don't know that formula, is CH4. And instead of saying like 130 grams of methane gas or whatever it is, we're given volume, temperature, and pressure. And because of the ideal gas law, as long as we have volume, temperature, and pressure, we can always solve for moles. So same thing here, oxygen gas. Quantities are given in volume, temperature, and pressure. So we set up an equation, we solve for moles, look for limiting reactant, all that kind of stuff. The only difference here is instead of being given a mass to start with, we're given gas quantities to start with. So we're going to use the ideal gas law to solve for moles. So see if you can do at least the first part of this question, which would be setting up the balanced equation and solving for moles of everything. Do an equation like that. So to find the quantities, we're going to rearrange our gas equation, n equals PV over RT, and solve for n in each case. We can check our units. Everything's good except we've got to convert Celsius to kelvins. So we add 273 to all the Celsiuses. All right, so for methane, that's going to be 1.65 times 2.8 divided by 0.0821 divided by 298. 0.189, we'll say, moles. And for oxygen, it's 1.25 atmospheres times 35 liters divided by R and divided by temperature, which is what, 304? Did you get those numbers also? Similar? Okay. All right. So now we've got to figure out how much carbon dioxide is formed. What's the limiting reactant? Methane, right? It's a 1-to-2 ratio between methane and oxygen. We've got way more oxygen, almost 10 times as much oxygen. So methane's the limiting reactant. So if we make 0.189 moles of methane, how much carbon dioxide do we make? Same, because it's a 1-to-1 ratio. Yeah. Yeah. Okay. So now we can use the rest of the information in the problem here to figure out the volume of carbon dioxide. So the volume of carbon dioxide .189 moles times R and temperature is given as 15 degrees C, which is 288 K. And the pressure is 2.50 atmospheres. .189 times 0.0821 times 288 divided by 2. 1.79 liters. Or really, I guess should be 1.8 because we only have two significant figures, but that's fine. All right. So this seems like a big, complicated problem, but notice the only new thing we're doing is using the gas quantities to find moles, and then using moles to find one of the gas quantities, like volume. Everything else is the same as we've always been doing. We find, you get moles, use our equation, set up the equation, use the mole ratio. All that stuff is the same from the last chapter. All that's changing now is we're using these volume and pressure and temperature quantities to solve for the gases. Okay, good so far. So please get started on the Chapter 5 homework because there's plenty of practice of this kind of stuff. Okay, so the other thing we can do with this idea is calculate the molar mass of a gas. Like figure out what kind of gas we have. Remember we said that in terms of how the gas law is set up, it doesn't really matter because all gases are going to behave the same. That's true, but they are going to weigh different. Right? They are going to have different masses. And so we can use gas quantities to actually figure out the identity of a gas, like what gas are we talking about kind of thing. So I don't think we need to go through this whole derivation, but let me show you a basic idea of what we're doing here. we're going to do just some substitutions, some algebraic substitutions. You can look in the book for how this is all done. I'll just show you the kind of where it starts. We know that N is number of moles. And we know that moles equals grams divided by molar mass. Right? Moles is grams divided by molar mass, which is grams per mole. If you divide grams by grams per mole, grams cancel and you're just left with moles. So moles is grams divided by molar mass. So we can use that in our equation. Instead of PV equals nRT, we can see PV equals grams divided by, and I don't know what they use for molar mass, but I'm going to use MW for molecular weight just so we don't confuse it with other stuff. All right. And so you can do the algebra, whatever, but when you do all that algebra, what you end up with is that molar mass equals grams times R times T divided by volume times pressure. And then we can notice that grams divided by volume is what? What's mass divided by volume? Yeah, that's density. So you'll see this equation written in the book sometimes as density times R times T over P. And that's a way to relate the molar mass to the density. This is useful because density is pretty easy to measure. You weigh something, you figure out how much volume there is, like we did with the percent NaCl thing in lab. You can figure out density pretty easily. So by finding the density of a sample of gas, you can determine what kind of gas it is, which is really useful for identification. It doesn't require any fancy instrumentation or anything like that. You can just know what a gas is by finding its molar mass. All right, so I don't want to do this problem. That's kind of boring. Let's do a different one. Let's look at this one. A 113 milliliter gas sample has a mass of 0.171 grams. And temperature of 32 degrees C. What is the molar mass? We could also say, what kind of a gas is it? We don't necessarily know. We'll talk about that in a second. But let's figure this out. So what is the molar mass? We have a volume, we have a mass, we have a pressure, and we have a temperature. So we have to use this kind of alternate form of the gas law here. Molar mass or molecular weight is the density times RT over the pressure. We do have to do some conversions here. So we're going to want to put this in liters, 0.113 liters. The pressure we want to have in atmospheres because of our R. So 721 divided by 760, 0.949. And then our temperature, as usually, we want in kelvins. So Density is mass divided by volume. Volume being in liters, so we can do that. So that is 0.171 grams divided by 0.113 liters. That gives us the density. Then we know R. And the temperature. And the pressure. Okay, everything should cancel here except for grams and moles. So let's check that. Liters cancels with liters, pressure with pressure, atmospheres, Kelvin with Kelvin. So we're left with grams on top and moles on bottom, which is grams per mole. That's molecular weight. So the molar mass is 39.9 grams per mole. Do we know what kind of a gas it is then?
Argon?
Probably argon. Right, 39.9 molecular weight, but not necessarily, right? Because we don't know how many different, if it were just made of one kind of atom, then sure, it's got to be argon. But what if it were like, not that this is probably not a real gas, but C3H3, right? That would be 39.9-ish, not quite. I don't know. Maybe there aren't any other possible gases, but we don't necessarily know because we're not told what atoms it's made out of. All right. So this part, this is kind of a big thing, this law of partial pressures. I think it's actually a lot easier than this. It just says that gases add together, and the pressures add together. We don't need to think of it in any trickier terms than that. If you've got a mixture of gases, each gas exerts an individual pressure, and the sum of all the gases is what we call the partial pressure. Or I'm sorry, the sum of all the gases is what we call the total pressure. Does that, you get that? Okay. So when you see problems with partial pressures, all you need to do is add them together. So let's take a look at like how that works in a sample problem. We're going to have a mixture of helium and oxygen in a scuba tank. And we're given some quantities of helium and some quantities of oxygen pumped into this 5-liter tank. Now, we can actually do this. Let's see, let's organize ourselves a little bit here. Here's our helium, do that in blue. Here's our oxygen. And then we're going to put all that into a tank together with a particular volume. And we'll be able to figure out the partial pressures based on the moles of each one. So we'll solve for moles. Let's do that. Moles of helium using the ideal gas law, and then moles of oxygen using the ideal gas law. So this side of the room do oxygen, this side of the room do helium. All right, who's got helium? You gotta find some moles of helium. 1.06. Did we get something different? Does this side agree? 1.06? Because I didn't do it, so I don't know. 1.8? 1.88? 1. I guess I should look at it.
Oh, never mind, yeah.
Okay, we'll go with 1.88. What about oxygen? Who's got it? What? 0.49? I got a third significant figure on there. I guess it shouldn't be, right? So we'll call it 4. We'll just call it 0.49. You're right. We only have 2 in this problem, so we should probably change this one too. This should be 1.9. All right, so we've got moles of each. Now they're being put into this new container. So the new container is going to have a new volume and a new pressure. We're assuming temperature is staying the same, I guess. So we can calculate the partial pressure of each of these based on their number of moles. So the partial pressure that each of these exerts in that final tank, that 5-liter tank, is now this new tank. So we can say for helium, the partial pressure is going to be that, just that. So 1.9 moles times R and the temperature, which is we're going to say is staying the same. And then the new volume is 5 liters. Partial pressure of oxygen, going to do the same thing, but with that other number of moles. So somebody get that one? The helium pressure? What does that come out to? What is that? 9.2? 9.3, we'll call it maybe. That's going to be atmospheres. And what about the oxygen pressure? All right. So since we only use the amounts of each of those gases to calculate that, those are called partial pressures. And that means the total pressure in the container is just going to be the sum of the partial pressures. So the total pressure is going to be 11.7 atmospheres. And that's the idea of partial pressure, that the individual gases, you can calculate their own pressure. Each gas is going to exert its own pressure, and then the sum of all of them is the total pressure in the tank. We can use this, we can figure this out in some other ways as well, using mole fraction. This idea of mole fraction is just the ratio of the moles of a substance to the total. So it's kind of like a percentage without multiplying by 100%. So if you've got 10 moles of gas total, you got 3 moles of one gas and 7 moles of the other. The mole fraction of the first one is 0.3, and the mole fraction of the second one is 0.7. Does that show how that works? So we can kind of interchange these, because if we go back to what we did up here, the only thing that changed between these two we can kind of say this is the same, right? And the only thing that changed was the moles. So if we know a mole fraction, that is what fraction of one is to the whole, then we know the partial pressures, or we can figure out the partial pressures. And also the other way around. If we measure the partial pressures, if we know the partial pressures, we can figure out the mole fractions as well. Anthony? Can you get him? Can you turn your movie down? It's a little loud. Thanks. All right, so the partial pressure of oxygen was observed to be this, right? 156 torr in air. And you're given the total pressure, what's the mole fraction? So the mole fraction is going to be exactly proportional to the partial pressure fraction. In other words, 156 divided by 743 is whatever it is. Let's see. .210. And that's going to be the mole fraction. So that means that I think if I did that right, yeah. That's the mole fraction of oxygen. That's how much oxygen is in the total mix. What percent? We would say that mix is 21% oxygen. So by moles and by pressures kind of goes hand in hand. Those mean the same things. Let's try this in a little bit bigger, a little bit different problem. And then we'll talk about why we care about this and where this comes up. Mole fraction of nitrogen is 0.78. So we're given the mole fraction. What is the partial pressure of nitrogen in air if the total pressure is 760 torr? So before you start on this, what do you think you need to do here? How can we find the partial pressure of nitrogen if we're given just a mole fraction and a total pressure? Yeah. Yeah, you're just going to multiply the two together. So we've got the fraction, kind of like a percentage, and we've got the total pressure. So the partial pressure is just going to be the percentage, basically. Partial pressure is the mole fraction times the total pressure. This is unitless, no units, times the total pressure. I always get confused with the partial pressure and mole fraction stuff. It's like different terms. It kind of sounds weird. That's kind of why I presented it this way. Just think of it as like a percentage. You just want to know how much of this there is relative to the total. And whether we're talking about moles, amounts of moles, or whether we're talking about amounts of pressure, it's the same. It's just how much of this is there relative to the total. What's the fraction of this compared to the total? The reason we care about this, or one of the reasons we care about this, is when it comes to collecting and measuring gases. You probably haven't given this a whole lot of thought, but if you want to collect a gas, it's not necessarily the most obvious thing to do. Like, how are you going to get the gas? One way, you can't just have it fill a container because it would just come out of the container. Even a balloon, it's got to have a certain pressure. That's one way to do it, I suppose. But one of the important parts about collecting a gas and measuring it is you got to make sure that the thing that you're collecting it in doesn't have anything in there to begin with. So if you've got something that's filled with air, and then you want to collect a gas in there, that's not really good because you don't know how much air is in there versus how much gas. So one way this is done is called over water, collecting a gas over water. Here's an example of zinc reacting with HCl, right, redox reaction. that produces hydrogen gas. You did this reaction probably last week. And then the hydrogen gas bubbles up through this tube, and you put it in kind of an overturned beaker that's been filled with water. As the gas is produced, it displaces the water in the tube, pushes the water down, and then you know how much water is collected because you know the volume here. So you can like measure how much is in there. The problem with this method is that whatever this liquid is also going to have some vapor. So as you can see in this picture, maybe it's kind of small, but this is not pure hydrogen gas in here. There's also some water vapor. So how do you figure out how much hydrogen gas you've collected if there's also water vapor in there? And the answer is you subtract for the partial pressure of water. So you can look up on a table like this and see what is the pressure of water at certain temperatures. And then you can subtract that out to account for it because partial pressures add to a total pressure. So we can solve a problem like this. Potassium chlorate decomposes to make oxygen gas. The oxygen was displaced water, or just the oxygen was collected over water, displacing water at a total pressure of 754 torr. Calculate how much oxygen was produced and then how much KClO3 was decomposed, assuming a stoichiometric decomposition. So normally we would say, okay, we got to solve for moles of oxygen. We've got pressure, temperature, volume. We can solve for moles. The thing that's a little tricky is because of this water thing, this is a total pressure, but we also have a pressure of water to deal with. So that means we can't only use that total pressure number. We have to figure out what's just the pressure of oxygen. The total pressure is going to be the pressure of oxygen and the pressure of the water vapor. That's what the partial pressure thing tells us. So because we know the temperature and we know the water vapor, we can subtract that out of the total. So the total pressure is 754 torr. And the pressure of oxygen is 21. So the pressure for just oxygen is going to be 733. Right, 754 minus 21. Now we can do the rest of the problem just as we did before. So why don't you do that? See if you can do this one. We've got a pressure now, we've got a temperature, we've got a volume. We can solve for moles of oxygen. And then we can figure out the mass of KClO3 that we started with, using our stoichiometry calculations from the last chapter. So see if you can do that now that we have a partial pressure. Let me know. see some like puzzled looks. Anybody figure out the moles yet for oxygen? Right, because it's in the whole, gas always fills its whole container. Oh, you know, we got to convert our pressure here. What's number 0? 22. Did we get that number yet?
Yeah,
1026. Does that sound right? Yeah? All right, great. So now we've got moles of oxygen. Oops. So we can go back in the equation. Get moles of potassium chlorate. And finish it up. Let's do that down here. So 0.026 moles of oxygen. Our molar ratio is 2 to 3. And then the molar mass of potassium chlorate. Did anybody get that yet? 122.5. Thank you. What does that all come out to? 2.12. That's going to be grams. All right. We good about that so far? Maybe. It's been kind of a long day, so we've gone through a lot. But you know, you can practice these things. But I want you to think about what is the same about this kind of problem. So first, we got moles from a pressure, a volume, and a temperature. That's what we've been doing for the last few pages, at least, of notes today. We get pressure, volume, and temperature, and we can solve for moles, which allows us to do those calculations in the chemical equation. The difference here is because we noticed that it was over water, we had to account for that initially by subtracting the water. So I want to pull up the book here. So I can show you what some problems like that are going to look like and how sometimes it's really not that obvious. So here's an example. So imagine a problem like this just kind of in the middle of an exam. oxygen gas emitted is collected over water at temperature 293, total pressure of 755.2. Total of this much gas is collected, 1 mass is formed. And it would be totally reasonable and easy to just start plugging in those numbers and say, okay, I've got a pressure, I've got a temperature, I've got a volume, I'll solve for moles and convert to grams. You'd be wrong. I mean, you'd get partial credit, but you'd be wrong because you missed this one phrase. Right? Because this gas is collected over water, we have to remember to subtract out that partial pressure of water vapor. Now, that's not a number that you would need to know off the top of your head, but you'd have to look back at a table like this. So 293K, is that what it said, or 295K? 293K is 20 degrees C. So we'd have to look up at a table like this and say, okay, 17.55 millimeters of mercury, we got to subtract. So, yep, you just subtract it before you go. Minus, what did I say that number was? I don't remember. 17.55. $137.7. And that's going to be our partial pressure of oxygen. So we have to remember to subtract out that vapor pressure of water first before we go do the rest of the equation or the rest of the problem. Otherwise, we're going to be wrong. And so then this is the pressure that we use, convert to atmospheres, and plug into the ideal gas law to get moles and then to get grams. Yeah.
We're going to have that chart available.
Yeah, so you either the chart or just the number. Yeah, you won't have to know those numbers. Right. All right, so let's look at another one here. Let's do one more of these before we get going. This is not one that's in the homework, I think. And then what's going to be left for this chapter that we'll finish up on Thursday is kinetic molecular theory of gases, which is the theory. Why is all this stuff happening? What do gas molecules do that cause all these effects? So let's try this one. See if you can do it on your own, and then we'll go through it together. Carbon monoxide reacting with hydrogen gas. We're given a reaction vessel at a temperature and a volume with a partial pressure of each gas. And we've got to figure out the theoretical yield of methanol. While we're working on that, I'm going to pull up the lab for tomorrow. How's this one going? So what'd you get for the moles of each of these? What do you get for moles of CO? What do you get? And what about hydrogen? Did we get that one? 0.298. Does that look right for those of you who are also doing it? Okay. All right, so which one's limiting? Look at those two. Which one's limiting? Hydrogen's limiting, right? Because we're supposed to have twice as many moles of hydrogen as CO, as carbon monoxide. And instead we have, I don't know, not twice as many, less than twice as many. So we're going to use the hydrogen number to figure out the theoretical yield. 0.0299 divided by 2, because it's 2 to 1. .015 moles theoretical yield. And then we can convert that to grams based on the molar mass. So 32, is that right? 22. No, 32. Yeah, 32, right? So that's our theoretical yield. And this makes something like this a lot easier dealing with pressures from an experimental standpoint. If you're doing this, like you're actually putting gas into a thing to do a reaction, so all you have to do is open up your gas valve until 232 comes out, close it, and then add another 397 or whatever the total pressure adds up to. And then you know you have those appropriate amounts. So that's how you would mix gases in a practical way. Instead of weighing them out on a balance or something, you would just use the partial pressures and you'd add this much pressure to this one, this much pressure to this one. Do you have a question?
Yeah, when you were solving for when you got 0.013 moles, and it's like the N equals PV over RT.
Right.
What did you use for volume?
Volume is 1.5 liters, the volume of the container. See that there? 1.5 liter reaction vessel.
And for the PV, you have 0.305, something like that.
For P?
Yeah.
For pressure? Yeah, I think so. Let's see, 232 divided by 760, 0.305, yeah. Did you get something?
Yeah, I got it.
All right, let's take a look at your stuff afterwards. So for lab tomorrow, we're kind of behind. We're a little behind, not too bad, but we're a little behind. So we haven't done this chapter 7 stuff yet. So don't do the pre-lab for tomorrow. We'll just make that part of the lab report because we're going to go through this stuff on Thursday, and then we'll do it. So plus you've got 2 lab reports due tomorrow anyway, so you probably don't need another thing to do anyway. So yeah, we'll turn those lab reports in at the beginning of class tomorrow. Don't worry about the pre-lab. It's a pretty good lab. We just burn stuff. Don't do the pre-lab because we haven't done this stuff yet. And see you all tomorrow.
I have a question about